Module 2, Relational Summary Lecture GSE2, Seeds of Sustainability. We've covered the implications of the huge amounts of liquid water in the southern hemisphere of what really should be called the planet water, not the planet Earth, and how they've regulated and stabilized the climate for millions of years, enabling human beings and our civilizations to flourish. What we need to talk about now are the big white elephants in the room, the masses of solid water, the frozen water that also dominates this hemisphere. The obvious elephant is the continent of Antarctica, but it isn't the only land of perpetual snow and ice in the south. Glacial ice is said to be the largest reservoir of fresh water on Earth, and despite the dearth of the Earth in the southern hemisphere, we can find miles and miles of ice glaciers in the south, from two of the most accessible glaciers in the world, Franz Josef and Fox, near the rainy west coast of New Zealand's South Island, to Kenya's Mount Kenya, Mount Kilimanjaro in Tanzania, and the Ruwenzori Mountains of Uganda, and westward to Bolivia, Venezuela, Colombia, Ecuador, Peru, and Chile, and most famously, Argentina, where trekkers have been visiting the towering walls of ice, Perito Moreno, since the expeditions of Alexander von Humboldt and Henri Bonpland during the years 1799 to 1824. Many of these, once considered almost permanent glaciers, tower above tropical and subtropical rainforests and supply most of the fresh water that communities below them depend on. I had the privilege of eating snow near Pico Humboldt and Pico Bonpland, glaciers named after the famous scientists and explorers, in the Sierra Nevada de Merida in the Venezuelan Andes on a Harvard Botanical expedition in 1984, where we traveled mainly to explore rainforest ecology. It was there, over 160 years after Humboldt explored them for the Europeans, that I first learned that climate change was a serious issue. It was an issue that Humboldt himself wrote about during those expeditions to those very locations. Yes, anthropogenic climate change has been a topic of concern for over a century. Scientists like Humboldt, who was obsessed with data collection and measurement, were already witnessing the signs that the glaciers were not permanent at all and could be affected by our activities. Now, the problem with glaciers in New Zealand and Africa and South America and, of course, Antarctica, to say nothing of the glaciers in the northern hemisphere, is that when that ice and snow melts, it absolutely raises sea level. The ubiquitous misguided and misleading memes on social media showing how ice melting doesn't affect water volume are trying to confuse people about sea ice. Land ice is quite another matter entirely. According to the website Climate Feedback, quote, Greenland lost around 3,800 billion tons of ice between 1992 and 2018, while Antarctica lost about 2,700 billion tons between 1992 and 2017, together raising global sea level by about 18 millimeters over that time span. There's another problem facing us as the ice warms up and melts and the seas gain heat that has nowhere to go. Remember, by the laws of physics, heat always goes to cold and always rises. Quote, there's also one more process that is a primary contributor to sea level rise, thermal expansion. Like other fluids, seawater expands as its temperature increases. And this means that as the oceans warm, their volume expands enough to raise sea level measurably, end quote. Not something we think about every day because unless we're observing the phase change of liquid water to steam, we rarely see the expansion as dense cold water turns into less dense warm water. It's subtle when viewing a glass of slowly warming ice water, far too subtle for most of us. But cumulatively, it puts us in a lot of hot water. And these effects of melting glaciers and ice and snow are just the tip of the iceberg, if you'll excuse the pun. We're also looking at an unprecedented acceleration of the sixth mass extinction, which is having profound effects on the entire food web. And it gets worse. The southern oceans aren't just being inundated with current disrupting and migration confounding amounts of ice cold, but inevitably warming and expanding fresh water, changing the salinity in wildlife and fishery devastating ways. And they aren't just being inundated with CO2 gases that are lowering the pH to exoskeleton dissolving and bone chilling, or is it bone warming, levels. But they're also being filled with the carbon of another form, microplastics. You see, the impact of the fossil fuel era isn't just the amount of carbon gases we've been putting in the atmosphere and hydrosphere. It's also about the carbon liquids and solids we pour and dump and spew into our oceans. Earth.org recently had an eye-opening article on the havoc that microplastics are having on the forests of phytoplankton such as to impede the ocean's biotic carbon sequestration. The article reports, quote, "The ocean is at the front line of mitigating the climate crisis. Making up over 70% of the Earth's surface, the ocean plays a crucial role in controlling the global climate system through, among other processes, absorbing and storing carbon dioxide from the atmosphere. Such processes are made possible by microscopic single-celled aquatic creatures called phytoplankton. These tiny organisms, dubbed the ocean's invisible forests, generate about half the atmosphere's oxygen and sequester as much carbon dioxide per year as all land plants. Similar to land plants, phytoplankton soaks up sunlight and captures carbon dioxide for photosynthesis, producing oxygen. Just as trees store carbon in their trunks, leaves, stems, and roots, phytoplankton stores carbon in their bodies. When they die and sink to the sea floor, the trapped carbon in their bodies also sinks deep into the ocean's waters. Phytoplankton is at the base of the marine food web, meaning that they provide marine creatures, from the tiny animal-like zooplankton to whales, with food. When other more massive sea creatures eat phytoplankton and zooplankton, the carbon in their bodies is transferred to these animals. This carbon will then settle into marine sediments on the ocean floor in fecal pellets and animal carcasses. The processes of carbon removal from the atmosphere and its absorption into seafloor sediments is called the biological pump. And through this process, the ocean regulates the Earth's climate. However, the plastic waste crisis will have a detrimental impact on the climate. Every year, 8 million tons of plastic enter the world's oceans, which are categorized into micro and nanoplastics. Scientists continue to examine the effects of plastic debris on the biological pump process. And further, about 4/5 of all trash in the ocean comes from land-based activity, like poor waste management, litter, and construction. A recent study published in the journal Marine Pollution Bulletin found that plastic pollution in the ocean may negatively affect the ocean's role in removing atmospheric carbon dioxide, which will eventually disturb the global carbon cycle. Microplastics in the ocean can negatively impact the growth of phytoplankton. Moreover, the abundance of microplastics, like those of the plastic garbage patches comprising thousands of tons of floating microplastics, forms a layer on the surface of the ocean, affecting light transmission and disturbing the efficiency of phytoplankton photosynthesis. Marine microplastics also affect the development and reproduction of phytoplankton and thus interfere with the process of organic oceanic carbon storage. Additionally, the study highlighted how microplastics negatively affect zooplankton. Zooplankton, which feed on phytoplankton, is one of the intermediaries between phytoplankton and other large aquatic animals. Zooplankton eating phytoplankton ensures the prevention of the stored carbon from re-entering the water and atmosphere. However, the plastic waste crisis disrupts this process. According to a 2015 study on a member of zooplankton known as copepods, microplastics can reduce copepods' uptake and consumption of carbon. After eating microplastics, their carbon biomass intake was reduced by 40%. Microplastics, the study reported, may also alter the sinking rates of zooplankton's fecal pellets. The pellets contaminated with microplastics sink slower than uncontaminated pellets. The study, however, points out that further research on the effects of microplastics on fecal pellets is still needed, noting that there are only a few studies conducted on the topic. Because microplastics sink to the ocean floor in these fecal pellets, it may also affect ocean carbon stock, affecting the circulation of organic matter and nutrients in deep ocean water. Troublingly, the study notes that the potential impact of microplastics in the ocean's deepest points remains to a large extent unclear. More studies are needed to establish a firmer link between marine plastic pollution and the biological pump. However, what is clear is that the marine plastic crisis may make our climate worse. In fact, a study conducted in 2014 estimated that nearly 99% of the ocean's plastic was unaccounted for, suggesting that creatures such as phytoplankton and other larger creatures are eating plastic, affecting their ability to absorb and store carbon, end quote. Of course, the solution to all these dire problems is not to eliminate carbon, not to eliminate plastics, but simply to eliminate the use of fossil carbon altogether. and replace it all with biodegradable and rapidly assimilable forms of carbon that help the ocean do its climate regulating job. Plant-based biodegradable plastics that could feed the zooplankton rather than harming them. Plant-based plastics that positively affect their ability to absorb and store carbon are nothing new. Take the development of peanut plastics, for example. It is said that the agricultural chemist George Washington Carver saved the South, by which they really mean the south of the north, the plantations of the southern United States, at 27 and 39 degrees north latitude. But the way he did it holds the key to reversing climate change and saving the southern hemisphere's oceans. This esteemed son of slaves merged indigenous knowledge, métis, and the science he pioneered at Tuskegee University, technique, to work with nature, in particularly the Leguminosae family of plants, including the peanut, to draw down a gas from the atmosphere, nitrogen, so that soils could flourish and carbon could be drawn down and food could grow. Now, Carver was a drawdown pioneer, but he wasn't just a nitrogen drawdown champion. He also invented technologies that could draw down fossil CO2 and replace fossil carbon so it doesn't accumulate on the land and in the sea. And one of his discoveries was how to make plastic from peanuts, an innovation of such value that Henry Ford brought him up to Dearborn, Michigan to explore a business venture based on it. As the History Channel recounts, quote, like Carver, Ford was deeply interested in the regenerative properties of soil and the potential of alternative crops such as peanuts and soybeans to produce plastics, paint, fuel, and other products. Ford had long believed that the world would eventually need a substitute for gasoline and supported the production of ethanol, or grain alcohol, as an alternative fuel. In 1942, he would showcase a car with a lightweight plastic body made from soybeans. Ford and Carver began corresponding via letter in 1934, and their mutual admiration deepened after Carver made a visit to Michigan in 1937. As Douglas Brinkley writes in Wheels for the World, his history of Ford, the automaker donated generously to the Tuskegee Institute, helping finance Carver's experiments, and Carver in turn spent a period of time helping to oversee crops at the Ford plantation in Wayes, Georgia. By the time World War II began, Ford had made repeated journeys to Tuskegee to convince Carver to come to Dearborn and help him develop a synthetic rubber to help compensate for wartime rubber shortages. Carver arrived on July 19, 1942, and set up a laboratory in an old waterworks building in Dearborn. He and Ford experimented with different crops, including sweet potatoes and dandelions, eventually devising a way to make the rubber substitute from goldenrod, a plant weed. Carver died in January 1943, Ford in April 1947, but the relationship between their two institutions continued to flourish, end quote. Not quite sure to make of the statement continued to flourish. As late as 2018, when National Geographic launched its Planet or Plastic campaign, they reported that, quote, more than 18 trillion pounds of plastic have been produced to date, and 18 billion pounds of plastic flows into the ocean every year. It ensnares the marine animals we cherish and the fish we put on our plates. It appears in the table salt we use, and it's even found in our own bodies. As more research on the impact of using so much plastic comes to light, consumers and manufacturers are left scrambling for an alternative to the ubiquitous material, and bioplastics have emerged as a potential alternative, end quote. But the article goes on to say, quote, the argument for bio-based plastics is the inherent value of reducing the carbon footprint. About 8% of the world's oil is used to make plastic, and proponents of bioplastic often tout a reduction in this use as a major benefit. This argument rests on the idea that if a plastic item does release carbon once it's discarded, as it degrades, bioplastic will add less carbon to the atmosphere because they're simply returning the carbon the plant sucked up while growing instead of releasing carbon that had previously been trapped underground in the form of oil, end quote. The problem with this is threefold with today's bioplastics, like the PLA we use in our 3D printer at PCGS. The first two are the types of plant we're using and the way we grow them. Most bioplastics, unfortunately, are made from, drumroll please, industrial agriculture corn. Others are made from sugar cane. And the way we grow these commodity crops uses intensive amounts of fossil fuels, pesticides, and fertilizers, and causes the biggest problem of all, soil degradation. That is a problem with oil. The biggest problem of oil, the biggest problem of oil. Biggest problem of all, biggest problem of soil degradation. Yeah, commit it to memory. The biggest problem of all, soil degradation. So such bioplastics are not in any way a net win. The third problem is that to be useful, these plastics are necessarily hardened. So as Nat Geo tells us, quote, depending on the type of polymer used to make it, discarded bioplastic must either be sent to a landfill, recycled like many but not all petroleum-based plastics, or sent to an industrial compost site. Industrial composting is necessary to heat the bioplastic to a high enough temperature that allows microbes to break it down. Without that intense heat, bioplastics won't degrade on their own in a meaningful time frame, either in a landfill or even your home compost heap. If they end up in marine environments, they'll function similarly to petroleum-based plastic, breaking down into micro-sized pieces lasting for decades and presenting a danger to marine life. Quote, if PLA bioplastic does leak out, it also will not biodegrade in the ocean, says Jembeck. When National Geographic launched its Planet or Plastic campaign, they reported that, quote, more than 18 trillion pounds of plastic have been produced to date, and 18 billion pounds of plastic flows into the ocean every year. It ensnares the marine animals we cherish and the fish we put on our plates. It appears in the table salt we use, and it's even found in our own bodies. As more research on the impact of using so much plastic comes to light, consumers and manufacturers are left scrambling for an alternative to the ubiquitous material, and bioplastics have emerged as a potential alternative, end quote. But the article goes on to say, quote, the argument for bio-based plastics is the inherent value of reducing the carbon footprint. About 8% of the world's oil is used to make plastic, and proponents of bioplastic often tout a reduction in this use as a major benefit. This argument rests on the idea that if a plastic item does release carbon once it's discarded, as it degrades, bioplastic will add less carbon to the atmosphere because they're simply returning the carbon the plant sucked up while growing instead of releasing carbon that had previously been trapped underground in the form of oil, end quote. The problem with this is threefold with today's bioplastics, like the PLA we use in our 3D printer at PCGS. The first two are the types of plant we're using and the way we grow them. Most bioplastics, unfortunately, are made from, drumroll please, industrial agriculture corn. Others are made from sugar cane. And the way we grow these commodity crops uses intensive amounts of fossil fuels, pesticides, and fertilizers, and causes the biggest problem of all, soil degradation. That is a problem with oil. The biggest problem of oil, the biggest problem of oil. Biggest problem of all, biggest problem of soil degradation. Yeah, commit it to memory. The biggest problem of all, soil degradation. So such bioplastics are not in any way a net win. The third problem is that to be useful, these plastics are necessarily hardened. So as Nat Geo tells us, quote, depending on the type of polymer used to make it, discarded bioplastic must either be sent to a landfill, recycled like many but not all petroleum-based plastics, or sent to an industrial compost site. Industrial composting is necessary to heat the bioplastic to a high enough temperature that allows microbes to break it down. Without that intense heat, bioplastics won't degrade on their own in a meaningful time frame, either in a landfill or even your home compost heap. If they end up in marine environments, they'll function similarly to petroleum-based plastic, breaking down into micro-sized pieces lasting for decades and presenting a danger to marine life. Quote, if PLA bioplastic does leak out, it also will not biodegrade in the ocean, says Jembeck. It's really not any different from those industrial polymers. It can be composted in an industrial facility, but if the town doesn't have one, then it's not any different, end quote. Dr. Carver's solution, as the prime example of a nexus-thinking agricultural chemist, could have negated all those issues. Peanuts are, as we've said, nitrogen-fixing perennials, though they're commercially grown as an annual for perverse reasons. And as such, they need no plowing, no chemical fertilizers, and technically they do not require herbicides or pesticides, which isn't to say that they aren't being used on them. As the National Peanut Board tells it, quote, it's important to understand that glyphosate is not used on peanuts during the season because it's not a Roundup-ready crop. According to Dr. Prosko, quote, growers do not apply glyphosate on peanuts during the growing season, but some farmers use glyphosate to manage weeds prior to planting. Dr. Prosko explains about two kinds of tillage practices used by Georgia's farmers, conventional and reduced or strip tillage. Using conventional tillage prior to planting, a farmer churns up or tills the ground to receive the seeds. This tilling process gets rid of the weeds, so herbicides such as glyphosate are not needed to clear the field of unwanted weeds. Reduced or strip tillage is a practice of minimizing soil disturbance and allowing crop residue, stubble, or weeds to remain on the ground. And Dr. Prosko said farmers who practiced reduced or strip tillage often do use glyphosate to manage unwanted weeds prior to planting season, end quote. We, of course, champion no-till farming as a drawdown solution for regenerative agriculture, but there are ways to do it without the awful glyphosate. Carver, with different goals born of environmental justice concerns, would have seen to that with his incipient permaculture instincts. So the peanut plastic that he invented, and a host of other bioplastics he introduced to Henry Ford, including hemp and soy plastics, out of which Ford eventually built prototype car bodies, could have saved the South and the North in many other ways. But as with the death of Walt Disney derailing the original plans for Epcot to become a real working city of sustainability, the deaths of Carver and Ford put their dreams in the hands of people who didn't have the same vision and were subject to the retardation the politics of short-term profit inevitably creates. But the good news is that the ideas and the techniques were and are all there. In the intrigo for this section, we touched on drawdown number 47, bioplastics, with a first cost of $19 billion to retool, while reducing 4.3 gigatons of CO2. The book claims that regarding the net savings, the data is too indefinite to be modeled. But since conservative estimates show that total production of plastic in general is expected to grow from 311 million tons in 2014 to somewhere between 792 million to 1 billion tons by 2050, with more plastic in the sea than fish, biopolymers like those that Carver was working on are crucial because we're able to make the plastic out of the peanut shell waste products already in abundance. And our book informs us that the major constraint to the bioplastic solution is, quote, limited biomass feedstock available without additional land conversion. And land conversion, or landscape change, is a huge driver of climate change. So we don't want that. But I have firsthand experience with waste biomass to plastic production. I was part of the Google Science Fair judge team for 7 years and awarded a prize to Elif Bilgin, a 16-year-old Turkish student who I was able to bring on stage with me at a National Geographic event in Istanbul to demonstrate the bioplastic she made in her kitchen out of waste banana peels. And then we have kelp. Yep, kelp. Have you ever gone diving in a kelp forest? I had the privilege of doing so in San Diego next to Scripps Oceanographic Institute in the mid-'80s as part of my advanced open water scuba training, and then again off of Catalina Island near Los Angeles in the mid-'90s. And it's a riot of life. Bright orange Garibaldi fish, spotted leopard sharks, Abyssinian urchins, and otters and sea lions. There's something hidden behind every tree trunk of this giant algae. And it turns out that kelp grows super fast and is fantastic at sequestering carbon and has enormous economic potential as a source of food for people and livestock and fertilizer and, yes, oil. There are other fast-growing algae of interest. Almost everybody has been hearing about the potential to harvest algae for biofuels for years. In fact, it's a major focus of the research that our own Dr. Philippidis at PCGS is conducting with his students, and he has tanks of it growing in the engineering lab at USF. At the Arava Institute of Environmental Studies at Kibbutz Keturah in Israel, where I was on the courtesy faculty and taught biofuel workshops, they have row after row of massive glass tubes in the middle of the desert growing red algae, a simple microscopic organism with enormous potential. But I want to talk about giant algae, giant kelp, for a moment. Project Drawdown considers kelp to be one of the most important coastal and ocean sinks for carbon, able to pull 1 to 1.48 gigatons CO2 equivalent by 2050. Recent experiments near Catalina Island, where I used to dive in those spectacular forests, have shown that we don't have to disturb existing kelp forests, but have enormous potential to farm kelp in what are now barren patches of ocean. According to a report in Science and thesea.org, quote, researchers built a gridwork of pipes for the giant kelp to attach to. They then placed the platform off Catalina Island near Los Angeles. During the day, the platform stayed near the surface, providing plenty of sunlight. At night, it dropped to a depth of about 250 feet, immersing the kelp in nutrient-rich waters. The kelp grew by up to 2 to 3 feet per day, much faster than the patches that were grown in a more natural kelp environment, close to shore. More tests are being planned. If they work out, they could lead to full-scale kelp farming and a new source of energy, end quote. Of course, algae has been used as a source of oil forever, but that's because most of our petroleum comes from ancient algae deposits that rained down on the ocean floor and were buried and compressed and heated over millions of years. Yes, most of our fossil fuels come from algae. We've known for a long time how to replicate the process using laboratory heat and pressure and chemistry, but it hasn't been economically competitive until now, they say. But as the recent article, Algae to Crude Oil, Million-Year Natural Process Takes Minutes in the Lab, points out, a new, quote, wet algae process is being perfected that eliminates the expensive process of drying and powdering, obviates the need for hexane solvents to extract the oil, and can be run in a continuous rather than batch process, all of which can bring the costs down to parity or below. It's a bit like using a pressure cooker, only the pressures and temperatures we use are much higher, said Elliott, the lead researcher at the Department of Energy's Pacific Northwest National Laboratory. Quote, in a sense, we are duplicating the process in the earth that converted algae into oil over the course of millions of years. We're just doing it much, much faster, he says. In the UK, researchers say, quote, many millions of pounds are being invested in seaweed research from Vietnam to Israel to Chile because producing biofuels in the sea removes at a stroke many of the serious problems with conventional biofuels. Though important as greener alternatives to oil, many biofuels are produced from food crops, such as corn and sugar, which drives up global prices in a world where 1 billion people are already hungry. Biofuel production also consumes increasingly scarce fresh water, and the worst examples, those from palm oil, can produce more carbon dioxide than diesel. Quote, seaweed does not have any of those problems, says Phil Carrison, another marine scientist. Seaweed farming has even been shown to clean up the pollution from fish farms, and kelp grows far more quickly than land plants, turning sunlight into chemical energy 5 times more efficiently, end quote. The ocean is vast. Coastal regions are vast, and these industrial ecology nexus thinking approaches using seaweed and algae, particularly in the global south, which has so much sunlit water, create win-win solutions to provide healthy, clean food, energy, and water with zero waste that can also draw down the carbon. Those who lived in the age of promise that flourished before fossil fuels and fossil forms of carbon became the dominant proxy for power already supplied us with these seeds for sustainability. As we will see again and again throughout this course, illustrated in 1,000 different examples and anecdotes, like Dorothy and her friends in The Wizard of Oz, we've always had what we needed to get back home to Paradise Earth.